All right, so we are reviewing some of the work of home, so let's pull that up and let's talk about that. And please, if you're home, okay, I can hear you. Say, Mr. Grotsky, I have a question. Don't feel shy, okay, that you can't stop me midstream. I won't get that mad, okay? No, I won't be. I won't, decrease your grade that much this quarter by you interrupting me. Right? So you've got to weigh your options. No, come on, please. Say, Mr. Grotsky, I don't get that. I won't say, learn on your own. I won't give you a Khan Academy link or something like that, okay? No, I'm there to help you. Okay, so any case, let's go to the, I gotta share this, so give me a second or two, and let's do that. Let's get this up, and it's gonna go up. Nice. Sometimes things work out, and most of the time I'm tall. Now, let's go to not speciation. Let's go to the key here. Okay, so where we left off together, okay, is talking about the simple definitions of acids and bases, all right? And I just want to review that before we go forward. And we know that the earliest definition was the Argenius. So I'm going to write that up here, Argenius. Or it's Arrhenius because his H is silent. So people on the YouTube yell at me for that because I keep saying the H. And I feel like if there's an H there in the word, I should say it, right? I don't know. All right? So there's the Argenius definition. And of course, that was the earliest one, the most simplified version. Hey, to be an acid, you produce H pluses. Hey, to be a base, you produce hydroxides, okay? And of course, if you look at the common acids that they give you in the reference table, there's a what leading to scream to you that you've got a compound that gives off the H's. Hey, the H in front screams to you that those are Arrhenius acids. Hey, and they also give you common bases. If you notice, what's a base? Base is an ionic compound, okay? In the case of Arrhenius, that you have a hydroxide ion. Hydroxide ion, okay? And of course, when these guys dissolve, these are all strong bases for reasons we've explained already. These guys dissociate into a lot of hydroxides, okay? So that's what we have here. Good deal, all right? Now, we have recognized the fact that there are going to be some compounds, specifically, here's a great example, that's also a base. We learned yesterday that bases will push their electrons onto things and break bonds. Ammonia is a household cleaning agent because it is a base. It will break up grime. Windex, if you ever use Windex to clean windows, takes the grease and smudges off windows because the base will actually break the bonds of the fats or the grease layers. Windex's major component is this base, but it doesn't have a hydroxide. So there must be another definition that's more encompassing, that includes Arrhenius, or Arrhenius, and it's the Bronsted-Lowry. Bronsted-Lowry. So this is a better definition. And of course we learned this yesterday. That better definition means, hey, instead of just saying that H pluses are produced, we're going to donate these protons. Because we know that the H pluses are very reactive. They're very small and positive. They're heat-sinking missiles for pairs of electrons. So Bronsted-Lowry bases, they accept the H plus. And we talked about this yesterday. Ammonia has 5 valence electrons. And H brings 1. This is the NH3. That's a base that's in the table that's not an Arrhenius base, but a Bronsted-Lowry base. What makes it a base are these 2 lone pairs of electrons. Those 2 lone pairs of electrons are what a proton, which we should know is H plus, is a heat-sinking missile for. It wants to bond there. Don't forget, hydrogen is in the first energy shell. It wants 2 electrons to be stable. So this H plus, first of all, is attracted to this electron density that's negative. Hey, 2 electrons sitting there. This is a highly rich area of electrons. This H plus is going to be attracted to. And there's a pair right here for it to bond. And when it does bond, what does it make? That lone pair stays there. They say it's a coordinate covalent bond, but it's the same thing. Okay, and notice something. Nitrogen feels like it has 8. Remember from yesterday? These are non-metals. They don't transfer electrons. They're good at attracting. So they're fighting for them. We're going to do bonding. We did some this summer, but these are fighting for electrons. Hydrogen feels like it has to. It didn't gain to, but it's by sharing and fighting for that rope. Okay, that tug-of-war analogy I used yesterday. All these hydrogens feel like they have 2. And the nitrogen feels like it has 8, and you just made a molecule. But because you gained a positive, this whole thing is +1. This is the ammonium ion. Okay? And you'll say, okay, but how does that change the pH? Well, as we said yesterday, okay, that lone pair of ammonia is very, very attracted for the H of the water. So that lone pair in ammonia, okay, water can do this. So what happens to water is that it donates a proton, and we know something about water. Water has an electron deficient H. I've been saying it for 2 years. These electrons are pulled toward the oxygen, so you're dangling out here essentially protons. So if you've got an electron-rich area, when water hits, when the H hits, it's going to want to stay here to easily grab those 2. So this is a base because it accepts a pair. But think with me, if you sit it in water like Windex, by pulling an H off of water, yes, NH3 becomes NH4+. Always be careful of the charges. You're adding a proton, so the charge goes up in an H. You're not bringing any electrons with it. What happens to the water? It loses an H+, becomes a hydroxide. Oh! So ammonia produces OH minuses. So indirectly, this main ingredient Windex is producing a base, a hydroxide, that can react. Okay, so it's important. Now, we learned yesterday that this is a base because in the future, it has one more what? H. Which means it must have accepted. That's how we figure it out. Water is the acid because in the future, it has one less H, which means it must have been donating. And hello, put a double arrow here if you haven't. It's going the other way. How does OH become water? In the reverse, this guy must be donating its extra H. And why would OH accept? Why would OH accept? It's got what? 3 lone pairs. We're going to talk about these. It's got what? Electron density, and it's negative. So H plus is really going to be attracted to that to make water. Backwards. Now, we learned yesterday, hey, that's the base, that's the acid. In the reverse, this has to be the acid because when it goes this way, it has one less. And I draw that. But what are conjugate pairs? Conjugate pairs are the same chemical. I wrote this down. So the word conjugate, this, is the same chemical plus or minus 1H. So NH4 plus is an acid. What is its conjugate base? NH3. These are conjugate acid-base pairs. Look at water. This is the acid, this is the conjugate base. When I say conjugate base, I mean, hey, what's left over after it donates an H+. It's the remainder. So think of conjugate as what's left over. For instance, let's get rid of some of this. Hydrochloric acid. After it gives off an H+, what remains? Cl negative. That's the conjugate base. Hey, bicarbion, HCO3 negative. When it gives off an H+, what's left over? CO3 negative 2. Careful, you lost an H+ there. That's the conjugate base. That's the acid. That's the conjugate base. That's the acid, the conjugate base. I could do it in reverse. if CO3 -2 is the conjugate base, what's the conjugate acid? We always change by one H plus. What's the conjugate acid? Well, don't acids have H pluses to give off? The acid always has one more H plus than its conjugate base. So what's the conjugate acid of CO3 -2? HCO3 -1. That's the base. That's its conjugate acid. What's the conjugate acid of Cl negative? HCl, correct. So when I ask for the conjugate acid always has one more H plus than its base. Let me ask you this question at home and here, okay? So I'm going to give you a hard one, the hardest one I can give you. Okay, this is a skill you have to have. Let's get rid of these guys. I'm liking the red. The red's coming out nice, nice, nice. If I give you this, HPO4 -2, I want the conjugate acid of that. What would it be? That means that this is the base, and I want the conjugate acid.
PO4 -1.
You're saying no more H's?
Oh,
So if I
or
take
would
the...
it be with H? H2.
Well, if this is the base, and I want the conjugate acid,
Oh, H2.
right, you need a second H. So H2PO4 -1, correct, because you're adding H plus. That'd be the conjugate acid of that. Okay? Now let's check this out. I'm going to let you write that. These are just some skills you have to have. Okay. Now, so this went this way. This now is the conjugate acid, which means I'm going to ask for the conjugate base of it. What's the conjugate base of that? So if I'm asking the conjugate base of that, that's the acid. What's the conjugate base? PO4, because you lost the H. The PO4 negative what?
3.
Right. And so you can see that this guy can go both ways. That's why it's called amphoteric. It can be an acid or a base. Okay? So, going to the homework. Everyone good at home?
Wait, what's that called? Amphoteric?
Amphoteric means you can act as an acid or a base, right? Because if it goes this way, what just happened to it? Didn't it accept an H plus to go this way? So it's acting as an acid.
But then it can go the other way.
If it's going the other way, it's donating an H plus. So it also can act as an acid or a base. That's called amphoteric. Water can do the same. Water can become, right? Water can accept a proton, become H3O plus, lose a proton, and become OH minus. Water is amphoteric. Okay? Now, let's go on to the homework. Okay, the other sheet, that was your homework. Okay? And I'm not going to redo it, but how do you do it? It's very simple. HNO2 becomes NO2 minus. It has one less going this way. That means it must have donated a proton. That's your acid. Oh! If this is the acid, this must be the conjugate what? Base. So that's the base, that's the acid, and you're done. If you're confused, go in the reverse. So you must be able to pick out the acid and bases on both sides, and you must be able to do what? Identify your conjugate acid-base pairs. Conjugate. Who are my conjugates? Same chemical, differ by an H. Same chemical, differ by an H. Conjugate. These are my conjugate pairs. Same chemical, plus or minus an H. All right? Now, let's do the last one. This is a little more difficult because this one, I didn't give you the products. And if you noticed, I gave you what? Amphoteric. These guys can be what? Accepting or donating an H. So how do you know which one it is? You had to look up in table L, it's Ka. And what is Ka? Ka is equal to the what? Products over reactants. And who are the products in acid-base reactions? The H pluses. Higher the Ka, the more H pluses you have. So the larger Ka means that's going to be the acid. That one you had to look up. Which means that must be its what? I need a conjugate base, which is one less H. If this is the base, its conjugate acid has to have one more, and you go on from there. You definitely need to review that, go through that. It's not a difficult skill, but it's important. You'll see this all through chemistry. Whether it's an easier course in college, more difficult, you have to have that ability to look at those chemicals. Okay. And that's, of course, the key I gave you. Let's go back and finish page 1. I left some things out, okay? So let's do that. Let's go to here. So I'm going to erase some things that I did here. Okay, so now, going back to my definitions, okay, up here, okay, as I erase some of them in my craziness here. We said Bronston-Lowry was more encompassing, was a better definition than Argenius. Remember Argenius? Hey, to be a base, you produce OH minuses directly. Ah, this thing stinks. Okay, I'm almost. I need a new black one. All right. Nothing. Okay. Oh.
Through them already?
I've been through a lot of them because they don't work the way that I want them to. All right, I got 2 left. Okay. So OH minus. Ah, it's beautiful. Okay, that's a beauty. OH minus and H plus. They just say I make them. Bronston-Lowry says, well, they donate them. You donate them. For instance, NH3. Oh, what happened?
Now that's a long.
NH3, not loving that. NH3 doesn't fit that definition. Okay, well, hopefully this thing gets better because I'm going to throw it in a second. All right, now, we have a better definition that includes, there are exceptions to this guy, to Bronston-Lowry. Bronston-Lowry is not the best. So the best, all-encompassing definition of acid and bases is Lewis. The Lewis definition. The Lewis definition. Because this includes all things that are acid and bases. Okay? If you look back here, party people, we have some common acids. We can easily identify the Arrhenius acids. They have an H in front, they give off H pluses. That's an easy one. And they also do what? They actually don't just give them off in solution, as Arrhenius said, they donate them. Okay, party people. Looky here. There is a CO2. There is a CO2 parked right here. And CO2, okay, does not fit the Arrhenius definition because it can't produce H pluses. It doesn't have any. It doesn't fit the Bronston-Lowry definition because how can it donate an H plus if it doesn't have an H? Yet we know CO2 is an acidic compound. It can make a solution acidic. In fact, this is really important because as global warming, or I should say as climate change continues to increase the amount of CO2, or as CO2 increases in our environment by man-made burning of fossil fuels, okay, possibly a combination of natural and man-made causes, or both, it doesn't really matter. As CO2 increases, it hits our water. It makes our what? Water's acidic. That acidic will kill our phytoplankton. Phytoplankton produces 70% of our oxygen. We're going to kill ourselves as the CO2 rises because we're going to be killing off the organisms that produce most of our oxygen. People always think about clear-cutting plants, and the plants produce most of the oxygen. It's the phytoplankton, okay? But there's something else even more important to us. How about breathing? How important is breathing? I would say it's pretty important, okay? And we don't report it every morning. Today in a local community, there was hundreds of thousands of people died today because they forgot to breathe last night. It doesn't work that way. I forgot to breathe! Okay, it doesn't work that way. We have something called an autonomic nervous system, right? part of the old part of the brain, the medulla, that controls breathing, heart rate. We can force ourselves to breathe, but that nervous system, okay, makes sure that we keep breathing, which is a good thing. So how does it know when to breathe or take over? It does so by measuring how much acidity our blood has. If the CO2 hits our bloodstream, if we're not breathing enough, remember, the product of cellular respiration, how we get energy and ATP, is CO2 and water. We're taking glucose, proteins, carbohydrates, fats, and we make ATP, but the product of that is CO2. CO2 diffuses to the membrane because it's nonpolar, goes through our bloodstream. And it makes our blood acidic. And we have a proprioceptor in our aorta that measures the acidity level of our blood. And if it's too acidic, it triggers a nerve response to our old part of our brain to trigger breathing. And as we breathe, we push out the CO2 out of our blood, and our blood becomes less acidic. So it's important you realize that. So what is the Lewis definition? How is CO2 an acid and such an important component of our life and our ecosystem? Okay, well, the Lewis definition is very simple. Okay, now think with me for a second. We were talking about ammonia for a second. Let's put ammonia back up, or even put up, we had ammonia. We had NH3 and a lone pair. And we said it was a base. Why? The H plus was really attracted to that lone pair. Or put up what we know is the best base, a hydroxide ion. It's even negative. So it's going to attract an H plus because it's negative, electron rich, and there's a lone pair. Oh! Having a lone pair means that the H, who wants two electrons to be stable, can make a bond there. So the idea of being a Bronson-Lowry base, you accept protons. The Lewis definition really describes how it can do that. How does a base accept a proton? It must have an electron-rich area to attract the proton first, but two, and most importantly, it needs a pair of electrons. It needs a pair of electrons to go there to bond. It's not bringing them. Look over here. Here, this hydrogen brought one to the table, and nitrogen brought the other, and they have a pair. This guy's bringing no. We need a pair of electrons. It's already there. It needs to be stable. So, to be a Lewis acid, okay, you need to accept a pair of electrons. You are a electron pair acceptor. That's the best definition. Okay, so we say electron pair acceptor. Which is the same thing as H pluses come over. But you've got to have a lone pair there. It's not going to bond to one atom or one electron. It's got to be electron rich, but you've got to have a lone pair. If a lone pair is not there, the H can't do that. Look at methane. Methane looks like this. Methane has 4 bonded to H's. It has no lone pairs. Do you think methane is a base? Can methane accept an H? It has no lone pairs. It can't. Methane is not a base. Okay? So party people, what's a base then? If Lewis acids are electron pair acceptors, what's a base? Bases are doing what? They're donating electron pair. So these guys are electron pair donators. And that's the best definition. But the question rises, how does CO2 increase the acidity? Which we're going to find out lowers pH today. How does it make a solution more acidic? Okay, I can see that maybe it can accept, it's acting as an acid, right? So CO2 is an acid, so it's a what? It must be an electron pair acceptor. Bases are always donating the pair. So I want to draw what we call a mechanism. Hopefully with a black, I feel like I should use black marker here. Okay, so I want to draw a mechanism, okay, and show you very important mechanism of how CO2 increases the H plus. We talked about yesterday that acids increase this. Indirectly it does. So stay with me, okay? Let's see how CO2 can become or is and why it is an important Lewis acid that is threatening our oceans, threatening our air, and a very important part of our bloodstream in terms of monitoring when to breathe. I think that's pretty important. So here's CO2. Oh, I'm not happy with that. Let's try another one, the last one. Sometimes I get better with age. Ooh, okay, we'll do that one. CO2. Okay, not bad. So CO2. We got a winner here. This one is not as good. All right, let's do the Lewis dot diagram. Lewis dots are the same thing as the same Lewis, but in any case, I'm going to show you. We're going to do this at some point, but I need to get this far. So carbon has 4 valence electrons. Okay? It's in column 14. It needs 4 more electrons to fill its outermost shell of electrons, which is 8. Oxygen has 6. 1, 2, 3, 4, 5, 6. Here's another oxygen. 1, 2, 3, 4, 5, 6. Now I draw the dots or electrons this way to show you something. By sharing, and again, carbon and oxygen are really pulling on each other for electrons. So by sharing, carbon feels like it has 8. Remember that tug of war scenario? They're covalencing here. And by sharing, oxygen feels like it has an 8. So party people, that's how it works. Now in truth, we write it this way. We say carbon double bonds to the O. Oh yeah, Mark is working out now. I can feel it flowing. Okay, so that's what CO2 is. But I really didn't draw it as accurately as I should have. So I'm going to do it one more time. Who is real, compared to oxygen and carbon, who do you think's better at pulling on electrons? Remember, oxygen's way over here compared to carbon. Oxygen. So I'm going to readjust this. So actually, these pairs of electrons are pulled closer to the oxygen. We know oxygen's great at attracting electrons. It's the reason why it's the oxidation. Okay, so these guys are closer. So what does oxygen do to these pair of electrons? It pulls them outward. So oxygen is pulling on these electrons. It's not strong enough, like me and my 5th grader, to pull the rope away. It's not. But it's enough that it can pull the rope away a lot. So this is what really happens. So if these electrons are pulled away from the oxygen, can you guess what charge this is slightly? It's kind of losing its negative, so it must be a little what? If it's kind of losing its negatives as it's pulling away, what must this be? Positive. It's getting some, it's not a complete positive, but it's a little positive. Okay. So because of the structure of CO2, the carbon's a little positive. The protons don't have their electrons anymore. Kind of lost them. It didn't really lose them. In AP Bio, this is the most oxidized form of carbon. In any case, here comes water. Water, we know, has lone pairs, right? 2 lone pairs. And then it bonds with an H. Oh, this electron pair likes that positive. What did this just do? This carbon is going to accept a lone pair. Look at your definition. This carbon is going to do what? Accept a lone pair. It's acting as an acid. Okay, so what happens? This is called a mechanism. So what happens is this carbon bonds, lone pair jumps right there, bonds with the water, still has a lone pair here. This becomes positive because I'm sharing my electrons with another nucleus. These electrons used to be all mine. Now I'm sharing them, so I'm a little positive. Okay? This is a double bond with an O. I'm still going to put that there. 2 lone pairs. This side isn't changing. Okay? Now, careful. Watch what happens. How does bases break things up? We talked about this, right? Bases push their electrons on. Remember, this is the acid. The acid is accepting the electrons. This is the what? Base. What's the base do? It donates the pair. And hold on, if it's going to push a pair on, it's going to kick this pair, one of the pairs, back on. And the reason for that is carbon has to have 8. It can't have 10 electrons. So here's what happens. One of those pair of electrons, remember a pair of electrons is a bond, becomes an O, and now it has 3 pairs of electrons. Notice there was only 2 pairs here. By pushing this pair outward, I lose a bond. And because now I have extra electrons on this O without a carbon bonded to it, this is a negative. And one last exchange. Hey, this is a positive and negative. This H sloughs off and becomes a positive and is attracted to that negative and moves over there. And so what we have is a carbon double bonded to an O, 2 lone pairs, nothing new there. Single bonded to an O, but now has an H. And the structure, its shape, I'll go into another time. And this is a what? Single bonded to an O. I lost an H, it's just an OH. And of course I do have lone pairs on the O. And that's the mechanism. And you say, oh, okay, big deal, I made that. Well, there is a big deal to that, because that has a name. Okay, in fact, party people, if you look at table acids, can you recognize what it is? Isn't that H2, CO3? That's blurry. And look what they do here. They tell you in your reference table, this or that. Well, this really becomes that in water. So what we have here is this. So in water, because CO2 accepts a pair of electrons, it makes this H2, okay, I'm just simplifying, 2 H's, and what's left? CO3. That's called a carbonic acid. And what do you think it does in water? Oh, it's going to donate a proton. Oh, this holds on to a proton. Now, why can't it? It's got lone pairs, doesn't it? This becomes H3O plus. And the conjugate base of the, what's the conjugate base of this guy? One less would be what? HCO3. What's its charge? Right. It's the bicarb ion. Party people, indirectly, CO2 in water produces this. That is water holding on to a proton. It is the same as a proton. It's called a hydronium ion. H3O plus and H plus are the same. Okay, it's really important. I'm never going to test you on the mechanism. But I wanted to show you that CO2 is a Lewis acid because it accepts a pairs of electrons. It's an electron pair acceptor. The base here is the water, electron pair donor. It's the best definition. So there you go. CO2 is acidic, okay? And let's do a demonstration with it, okay? To actually see that it is. I have a pH, okay? I want to get this off for a second, and we'll get back to this and do more in a second. But I'm going to turn this off for a second. Stop my mirroring, okay, and I'm going to connect my pH probe, all right? It's sitting in water. Okay, it should connect at some point. There we go. And it's hard to see at home, so I'll make this bigger, maybe. Woo! Christmas. We have issues. All right. All right, I think it's big enough.
Are you sure?
Yeah, okay.
Kept going.
All right. Now, So what I'm going to do is step over this without breaking any wires. That's tough for me. Oh.
As you get stuck.
Yeah. All right, now, what I'm going to do is take this straw, and I extended it, all right, 2 straws in one. Very scientific. And I'm going to blow my respiratory gases, which is mostly CO2, water vapor, some oxygen, and some nitrogen, of course, into the beaker. So I'm going to turn this on. We're going to spin this. And all I'm doing is mixing the Wasser. Okay? And we should know at some point that this is a pH of neutral is 7. Okay, we're going to learn after this why the pH drops or increases. But I'm going to bubble CO2 right now. Okay? You should know from common that acidic solutions, okay, are lower than 7. I'll prove that in a few minutes. But I'm going to bubble CO2 here. So I'm going to blow out CO2. Okay, we got lower. Okay, I'm gonna, another breath. Okay, before I get faint, all right? So by me blowing CO2, the pH is dropping. And why? Because I'm adding eventually carbonic acid, who is producing protons that bond with water, and this pH probe is picking up the H pluses. I want to go a little farther though. I'm not satisfied. Look, Ma, no hands.
Well.
Okay, I think you get it. I lowered the pH. It's getting more acidic, okay, because I'm blowing in CO2. CO2 is a Lewis acid. The question is, though, why? And this is the next piece, okay? So we're going to pick this up. I'm going to give everyone a mass break, and then I'm going to go into pH, and which is the next couple of sheets. So please take a break. My students here are going to take a break, and we're going to pick up in 5 minutes the second part of this lecture, which will be explaining pH, and we'll be doing parts of the second sheet together. So please take a break.